Vision language models are changing how we interact with AI. On this channel, we experimented with multimodal models before, but those were large foundational models with billions of parameters like CogVLM that can't be easily fine-tuned on regular hardware. Well, today I'm taking you on a journey as I'm going to fine-tune my very first multimodal model, PaliGemma. PaliGemma can perform multiple vision tasks. It can be used for image captioning, visual question answering and OCR, but what makes it super interesting is its ability to perform object detection and instance segmentation. All you need to do is use the detect and segment keywords in your prompt. PaliGemma is a family of open source vision language models released by Google a few weeks ago. It integrates cGLEEP image encoder and Gemma 2B text decoder connected by projection layer. cGLEEP is a powerful model designed to understand both images and text. Similar to CLEEP, it features image and text encoders. It can be used for zero-shot image classification, image similarity clustering, and much more. Gemma is a family of lightweight, open-source text generation models from Google and specializes in tasks such as question answering and summarization. PaliGemma is pre-trained on image-text pairs, making it adaptable for fine-tuning. Google released a notebook demonstrating how to do it for image captioning, but I wanted to take it a step further. I spent probably dozens of hours trying to figure out how to modify this notebook to use it for custom object detection. Now, let me show you how I fine-tuned my very first VLM. As usual, I prepared a Google Colab so you can open it up in separate tab and follow along. The link to the code is in the description below, but you can also find it in our RoboFlow Notebooks repository. Just scroll down and look for fine-tune PaliGemma on object detection dataset and click Open in Colab button. Before we start, we need to gain access to PaliGemma model. This requires logging into Kaggle or creating an account if you don't have one and accepting the PaliGemma license. As you can see, I already done this. Now we can download one of pre-trained versions of PaliGemma. The versions differ in image resolution and the length of text sequence they accept. Due to the limited resources of Google Colab, we'll fine-tune the smallest one, PaliGemma 3B PT224. The next step is to configure our API keys. To download the model, we'll need our Kaggle username and Kaggle key. We can generate this in Kaggle settings panel by clicking the Create New Token button. This will download a JSON file containing all necessary information. To download the dataset, we need RoboFlow API key. We just click on the avatar in the upper right corner of RoboFlow UI and select API keys from the dropdown. After clicking Copy, our key will be in the clipboard. Next, we return to Google Colab and click the key icon in the left side panel to open Secrets tab. Please follow the instructions in the notebook and set all required values. In the end, your side panel should look just like mine. Now I'll run NVIDIA semi command to confirm that our Colab has GPU acceleration. To fine-tune PaliGemma, we'll need at least NVIDIA T4 with 16 GB of VRAM and 12 GB of RAM. You can verify this by clicking Runtime and selecting Change Runtime Type from the drop-down menu. Now, in the pop-up, you can just choose the hardware you like and click Save. Now it's time to install some external dependencies. The first is Supervision, a computer vision Swiss Army knife that we'll use among other things to visualize PaliGemma results and benchmark our fine-tuned model. The second is RoboFlow, which we'll use to download our dataset from RoboFlow Universe. I decided to use a dataset of handwritten digits and math operations. It's one of the datasets included in RoboFlow 100 dataset, a collection of 100 diverse datasets that you can use to benchmark zero-shot detection models. Side note, we benchmark PaliGemma on RF100, more on that later in the video. To download the dataset from RoboFlow Universe, click Download Dataset, select the desired format and click Continue. This will generate a code snippet which you can simply copy and paste into Google Colab. Now simply run the cell to download the dataset. While we wait for the dataset to download, let me tell you a little bit more about the required data format. To fine-tune PaliGemma, we'll need a dataset in JSONL format. It's similar to JSON, but each line is an independent JSON object. Each JSON contains three keys: image, prefix, and suffix. Image holds the path to associated image. Prefix is the prompt that we are going to send to the model, and suffix is the expected response. It's simple but versatile and allow us to fine-tune the model for various downstream tasks. When used for image captioning, the prefix could be describe the image and the suffix would be a description like a man with a dog. When used for VQA, visual question answering, the prefix could be what breed of the dog is it? And the suffix would be the answer, like a beagle. Object detection is where things get interesting. Do you remember the unusual result we got from pre-trained PaliGemma, where we asked it to detect dog? Similar to other tasks, we have a prefix and a suffix. For instance, the prefix is detect dog, where the keyword detect is critical. The suffix has a specific format, 4 consecutive log tags followed by desired class name. If there are multiple objects, another section appears separated by semicolon. We can also search for multiple classes by listing them in the prefix, once again separated by semicolons. Most of you probably already guessed that the 4 log tags define a location of the bounding box, but the format itself is quite surprising. Imagine an image with a detection defined by coordinates x1, x2, y1, and y2. The image has height h and the width w. The first thing we need to do is to set the coordinates in the right order. y1, x1, y2, x2. Renormalize the image by dividing them by h and w respectively and multiply them by 1024. Let's assume that in our case we got 300, 400, 500 and 600. We place each within a log tag, ensuring they are zero padded to form 4-digit sequences. Finally, we append the class name after the log tags. By the way, right now you can download any object detection dataset in this exact format. Go there, explore, the link is in the description. Now we can use Linux head command to print the first 5 lines of train and validation subsets. As described, each line is a separate JSON object containing keys image, prefix, and suffix. Let's select 25 samples from our training set and visualize them. We can see that each image contains only one object. This is quite important, and I will discuss this further at the end of the video when I will cover the limitations of PaliGemma. Most of the code you will see right now is pretty much the same as in Google AI Notebook I mentioned earlier. The changes I made were related to parsing and visualizing object detection results. The first step is to clone the Big Vision repository where Google released PaliGemma. The library is written in JAX, a deep learning framework, an alternative to TensorFlow and PyTorch. It offers automatic differentiation and just-in-time compilation, allowing for faster and more efficient model training. On our channel, we have a video showing the basics of JAX. If you're interested, the link is in the top right corner. Once everything is installed, we import JAX, Big Vision, and other necessary libraries. We also check what and how many GPUs and TPUs we have. In our case, of course, we have a single NVIDIA T4 GPU. To limit GPU memory consumption and enable fine-tuning in Google Colab, we'll use the smallest version of PaliGemma 3B PT224. Let's download the base model from Kaggle using pre-configured API keys. Importantly, you must accept PaliGemma license in model card on Kaggle. Without that, Kaggle will simply deny you the access to the model. The download itself will take several minutes, so let's use the magic of cinema to speed it up. PaliGemma has 3 billion parameters, 2 billion for Gemma language model and about 1 billion for the image encoder. Due to the limited resources available in Google Colab, we need to limit the number of trainable parameters and freeze the rest of them. We'll fine-tune only the attention layers of our language model. This, of course, will limit the trainability of our model, but at the same time protect us from out-of-memory exception that we all hate. We load our model into the GPU and print the layers that make up the model. Frozen layers have been loaded as float 16s and those to be trained as float 32. Time to work on data loaders. First, we'll prepare a few helper functions, process image that converts the input image to grayscale and resizes the image to the size required by the model, in our case 224 by 224. The preprocess tokens function that tokenizes and formats input text, applying attention mask to distinguish between prefix and suffix, and the postprocess tokens function that decodes model output back into human readable text. Next, we'll define the train and validation data loaders utilizing the functions above. We'll also set the sec length parameter, in our case it's 128, representing the total number of tokens generated for the model during the training. To enable batching, all examples need to have the same length. The prefix and the suffix will be joined, separated by the new line character. Overly long examples will be truncated, while short ones will be padded with zeros. This parameter directly impacts the memory usage. The higher it is, the more VRAM you will need. However, if your dataset have a lot of classes and because of that longer prefixes, you will need to make it higher anyway. I've made small modification to these functions compared to the original Google AI notebook, particularly in the validation data loader. It was not returning the ground truth, which we'll need for benchmarking the model, as you will see shortly. Here are a few examples from our dataset. It's worth checking if the text have been truncated to the overly long sequences, as we can see loading and parsing work correctly. Finally, we define the training and evaluation loops. The training loop includes a step function to calculate the loss per example and apply stochastic gradient descent to update the model's parameters. The evaluation loop includes a prediction function to make predictions on validation dataset and assess the model performance. Now that we are set up, let's fine-tune the model. The code runs the training loop for 64 steps, printing the learning rate and the loss for each step. Every 8 steps, the model prints its predictions for a selected subset of validation set. This lets us observe how the model's ability to detect objects improve over time. In the early stages of the training, we can even expect predictions that don't meet the required structure, have too many or too few log tags, no class or no semicolon between detections. As the training progresses, the model's predictions become steadily more accurate, and by step 64, detections should closely resemble the annotations provided by the training data. This process takes several minutes on T4 GPU. Of course, all those parameters are configurable and you should adjust them depending on your training set. Before we take a look at training results, I want to invite you to our upcoming community session. If you don't know, after every YouTube video, we organize a live stream where I answer your questions about the video, but also about computer vision in general. You can find the recordings of previous streams on our YouTube channel and the date and the time of the upcoming community session in the description below. Come by and say hi. See you there. Here's a sample of the results PaliGemma achieved on the images from the validation set. Out of 16 examples, the model made a mistake only once, confusing 5 with 8. The model's accuracy is also confirmed by mean average precision, calculated to be 0.9, and the confusion matrix, where, as you can see, almost all values are on the diagonal, which means that the vast majority of cases, objects were detected and assigned the correct class. Time to save our trained model and test it on new images. First, we save the model weights to the hard drive, then deploy them to RoboFlow Universe, selecting PaliGemma Freebie PT224 as the type. Similar to pulling weights, uploading them may take a while, but once the process is complete, your model version page should look like this. Okay, let's put our freshly trained model to the test. I handwrote few digits on a piece of paper, took pictures of them, and uploaded them to Gradio app where I deployed the model. As a prompt, I used the same text that was in the prefix of my dataset. All 3 digits were detected correctly. Interestingly, when we repeat our initial test and ask about detecting a dog, the model is still able to do it. This is a clear advantage of PaliGemma over traditional CNN-based detectors. When we fine-tune the model on custom dataset, it can still detect the object classes on which it was pre-trained. Unfortunately, when I upload an image containing multiple digits and mathematical operations, the model struggles. This isn't entirely surprising. After all, the original dataset did not contain a single sample where multiple symbols were seen at the same time, and I suspect that even state-of-the-art CNNs would have problems with detecting those objects without data augmentation. But without further ado, let's talk about problems that I encountered while playing with PaliGemma over the past few weeks. First of all, I have to come clean. I did a bit of cherry picking when it came to choosing the dataset. Originally, I planned to use poker cards dataset, by the way, also one of RF100 datasets. However, despite spending considerable time and applying creative augmentation techniques, I couldn't achieve a MAP over 0.25. It seems that the issue is related to the number of detections in a single image, and I have few theories about the cause. A large number of bounding boxes forces the model to generate longer sequences, in some cases longer than the allow length defined by seek length variable. I also suspect that the order of bounding boxes matters, so even if the model returns the correct bounding boxes but in different order than those defined in dataset suffix, the model gets simply confused. Or maybe in complicated cases like this, fine-tuning only the attention layer of the language model is not enough, or maybe we should even train a larger model. Either way, in the end, I decided to show you how to fine-tune PaliGemma on this specific case, but I think that you should be aware that this problem exists. And if any of you have an idea how to solve this problem, please let me know in the comment. I would be super grateful. Many of you have also asked me if PaliGemma can be used to automatically label your dataset. In the past, we've shown how to use zero-shot detectors like Grounding Dino or Yellow World to automatically annotate data. We even added this functionality to RoboFlow Editor. We tested PaliGemma on RF100 to evaluate its zero-shot capabilities, but they don't seem to be good enough, especially compared to models like Grounding Dino. For over 50% of dataset, PaliGemma achieved MAP equal to 0. Interestingly, this includes the vehicle detection dataset. PaliGemma scored high on Twitter posts, thermal dogs and people, coins, construction safety, and animals datasets, achieving over 50% MAP on each of them. This aligns with Google's statements about PaliGemma. It's a model that needs to be fine-tuned to achieve satisfactory results. And that's all for today. I highly encourage you to try and fine-tune PaliGemma on your own data. And remember, all datasets on RoboFlow Universe are right now accessible in JSONL format compatible with PaliGemma. If you'll have any problems or questions, let me know in the comments below, and I'll try to answer them during the upcoming community session, where we are going to talk about not only PaliGemma, but also latest YOLO v10. Fine-tuning PaliGemma was another challenging yet incredibly rewarding project that I had an opportunity to do on this channel. I wanted to go beyond classical CNN-based models for quite some time, and that's awesome to finally have an opportunity to do it. While PaliGemma is not perfect, and fine-tuning it on datasets with large amount of classes or high amount of bounding boxes per image is hard, it's a step in the right direction and opens the door for accessible, open source, easily fine-tunable multimodal models that anybody can run on their own GPU. And who knows where we are going to be next year. In the meantime, if you enjoyed the video, make sure to like and subscribe, and stay tuned for more computer vision content coming to this channel soon. My name is Peter, and I see you next time. Bye.